Calculus 2, Section 5.4, the fundamental theorem of calculus. This is the central theorem of integral calculus. It connects integration and differentiation. Let's write that down. It connects integration and differentiation. The integral and the derivative. This allows us to use antiderivatives instead of limits of Riemann sums to figure things out. So let's take an example. Suppose you've got the function f of x equals x squared on the interval from 0 to 1. Let's draw a picture. 0 to 1, x squared is just the parabola opening up. Let's call this 1, and of course this is 0. And if we take a bunch of intervals here, these rectangles, remember for a Riemann sum we can use whatever we like, so we're going to use the ones that are sort of easy. We want the limit of the Riemann sum, so it's the limit as n goes to infinity. This will make the partition go to 0 of the sum k going from 1 to n of the function at c sub k. We're going to pick the right-hand side of this interval times delta x sub k. So this is the limit as n goes to infinity of the sum k going from 1 to n. So the function is x squared. What are we going to put in, though? We're going to put in 1 over n, and then 2 over n, and then 3 over n. So this is going to count 1, 2, 3. So it's really going to be k over n. But since it's the function squared, it's k over n. That's our x squared. The delta x is going to be the maximum here, the 1, minus the 0 over n, or just 1 over n. So this is times the 1 over n. Let's work with this a little bit. We've got the limit as n goes to infinity, summation k equals 1 to n. It's going to be k squared, and I'm going to split this off, 1 over n squared times 1 over n. So we get the limit as n goes to infinity. Well, remember, n is going to be a constant, so this 1 over n cubed can be pulled out. And the summation from k going from 1 to n of k squared is n times 2n plus 1. I'm sorry, times n plus 1 times 2n plus 1, if that's the way you remembered, over 6. Okay. So then we take the limit as n goes to infinity, and we're going to multiply this thing out. We've got let's leave the n alone, but this is 2n squared. 2n and 1n is 3n, and 1 times 1 is 1, over n cubed. Put this underneath with the 6. 6n cubed. Okay, now let's distribute that n. So the limit as n goes to infinity of 2n cubed plus 3n squared plus n, this is supposed to be a plus 1, over 6n cubed. Now, if you remember how to take the limit of one of these, you divide everybody by 6 over n cubed, so this is really 2 over 6, because the n's cancel. But this 3n squared over 6n cubed is really 3 over 6n, which goes to 0. And then you get n over 6n cubed, which is 1 over 6n squared, which goes to 0. And this just adds up to 1/3. So that's finding the Riemann sum. It took like half a page. So let's do that without the Riemann sum. We're going to use the integral from a to b of f of x dx. The definite integral. This goes from 0 to 1. F of x is x squared dx. Well, what's the antiderivative of x squared? Well, so we're going to add 1 and divide by that new exponent. And we're going to evaluate this from 0 to 1. That notation means plug in a 1 cubed over 3, minus plug in a 0 cubed over 3, which is just 1/3. Notice you get the same answer. So, what it allows us to do, instead of going through all those limits, because this is pretty simple, just x squared, you can get this answer pretty easily if you can find the antiderivative of this integrand. This also leads us to the mean value theorem. Do you remember the mean value theorem, the MVT for differentiation? Remember that says if this function f is continuous on the interval from a to b, the closed interval, then there exists c such that f of c equals the slope f of b minus f of a over b minus a. And if you remember the picture that went along with that, they usually draw, it's like a curve like this. This is a and this is b. So this point, if you take the y2 minus y1 and x2 minus x1, there is then this line that has that slope. They say there's some point C where we have the same slope for that function. Oh, this should be f prime. That gives you the slope. F prime at C. The slope of the curve at C. That's the mean value theorem for differentiation. What is the mean value theorem for integration? That's our theorem 3. The mean value theorem for the definite integral. I guess I should say 4. The definite integral. Starts out the same. If f is continuous on the interval from a to b, then there exists a c such that, well, the c has to be an element of ab, closed interval, such that that function f of c equals 1 over b minus a times the definite integral from a to b of f of x dx. Well, do you remember that? That's that average value of a function. So if you have a function that does this, here's a and here's b. Remember, the integral gives you this area, and when you divide by 1 over b minus a, you're really dividing that up into pieces so that this c value will give you a number. I don't know if I can pick that very well. Maybe it's over here. The c value will give you an f of c that will be the horizontal line that has the same area under that curve. That was just my guess. Some's outside, some's inside. So it's the same idea, except now it's not the slope at that point. It's the average value of the function, which gives you that same area. Now this is used in many cases for helping prove stuff, so that you can prove the fundamental theorem of calculus, integral calculus, it's a T. And we're not going to prove that here, but it's used in many theorems as a part of a proof. Let me bring up a paper that has been typed in that will be able to follow this fundamental theorem of calculus. So I was going to write out my own, I guess, but this I thought was pretty good, and the pictures are so much nicer than I can do. This is from intuitivecalculus.com, and it's the fundamental theorem of calculus made clear once and for all. It's still not easy to make clear, I think. Simple theorem, but it has a very intimidating name. This theorem gives the integral its importance. The integral is more important, I think, than the derivative. But it took us to figure out the derivative, I guess, first to think about the integral. The fundamental theorem of calculus is two parts. First one is most important, they say. I don't know. It talks about the relationship between the derivative and the integral. How the heck could there be any relationship? Well, first of all, they say, let's be a little intuitive here. This green line is the function f, and it's drawn here sort of simply because it's all above the x-axis. Take 2 points on the x-axis, call one a and one x, and consider the area under the curve and above the x-axis from a to x. So it looks something like this. All this red shaded area here from a to x. Okay, if we take a smaller number than this x, call it x sub 1, we get a smaller area. Makes sense. And if we take a greater number, x sub 2, we get a bigger area. So this one, yeah, that's a little bit bigger. We can define then a function, an area function, call it a of x. This function will, given an x, output to the area under the curve. So if you give an x here, then you get this area from a to x. The x sub 1, the x sub 2, the x over here. It'll give you the area under the curve. So that's what we're going to call this, this area function, a of x. Now it depends upon what curve we're talking about, of course. If you remember, I think the definite integral from a to x, this is the definite integral of f of t dt. So we can define a of x then as this area under the curve from a to x of f of t dt. That's what we said the definite integral was. So this first part just says that the derivative of a must be the derivative of this integral, which is just the integrand f of x. Now there's a little more to that. because what you really need to do, and we'll talk about that in a second, is make sure this a, if that's a constant and this is only x, then this is true. But if it's not a constant and this is something like x squared for the other limit, then you've got to do something else. We'll look at a couple examples. So they're saying the derivative of a of x with respect to x equals that function f of x, the integrand of this definite integral. Remember that the derivative is the rate of change, and therefore the rate of change of the area is this function. So our function gives us the area under the curve, this geometric shape, and a prime, the derivative of a, will give us the rate of change of this area. And it's just this height from the x-axis up to the curve itself. That's what a prime is. That's what f of x is. F of x. This rate of change equals the height is all they're saying geometrically. So the second part, so this is really just a derivative in the integral that we're talking about here, the definite integral. What's also important here, they call them in this thing a primitive. The indefinite integral is a primitive. It's really the function we took the derivative of to get that the integrand. So the primitive of this function f of x is another function whose derivative is f of x. So we can always add some constant here and make a little different function. We call them the family of functions. And if we add a constant each time, different constant, we have a different function that we take the derivative of, but it still gives us the same answer because the derivative of a constant is 0. But let's put that constant in there. So if the difference between this function, one of these other, they call them primitives, the other form of a of x, this is a of x plus c. And so the difference between these two is just that constant, whatever that might be. Because this is one of the functions, the constant is 0. This is another function, the constant is c. And this is another way of saying the same thing, that this function a of x is also this integral from 0 to x of f of t dt. Let's see, that a could be 0. In fact, it could be anything, really, almost. In the first part, we used 0 to x to explain the intuition, but we could use any number. That's why they put an a in there. It doesn't make any difference. The lower limit does not appear in any result. That a is no place. The capital A is there, but no place is that a in any of these results here. So this replacing this previous function, instead of a of x, we're going to use the integral, the definite integral from a to x of f of t dt, put that in for this a of x. Back up here, the a of x here. So we're going to have this integral with an a equal to f of x plus c. We're just putting that in for the a of x. So the definite integral is really just one of the primitives, one of the antiderivatives of this f of t, add the constant c. So here we're getting the formula for calculating definite integrals. Just find an antiderivative with the plus c stuff. We already know how to find a lot of those. If we go from a to a, remember, the area under that curve is just 0. The area under just point here, a to a, is 0. And what is the area of a line? It's just 0. So to find out what C is, we say that that area, back here with this, a to a of f of t to t is 0. So you plug in a 0, that equals f of a plus x, plus c. Don't use the x here. So at a, c is equal to negative f of a. So let's plug that in here. We get the definite integral, but that's f of x plus c. But hold it, c from up here is a negative f of a. So really, if x equals b, for this top one, a to b, we got f of t to t, and instead of x, we're going to put a b. So the integral from a to b of f of t to t is f of b minus f of a. And that, they say, is really impressive. What happened to the c? The c's cancel because we just subtract them. This has a plus c, this has a plus c. So that's what we did with this x squared from 0 to 1. X squared dx, and we can do this f, capital F of 1 minus capital F of 0. Well, the capital F is the antiderivative of x squared, which is this x cubed over 3 plus some constant c. When you go from 0 to 1, you get the x cubed, or 1 cubed over 3 plus some constant c, minus 0 cubed over 3 minus, because we're distributing the negative, constant c. The c's cancel. Of course, 0 over 3 is just 0, and 1/3 is our answer. So you don't have to worry about those constants. And it gives the area of 1/3. Or you can use the Riemann sums, which can take a half a page. We use this notation for calculating this. The area, or the integral from a to b of f of x dx is this antiderivative f at x, but you evaluate that from a to b. This vertical line really means plug in a b minus plug in an a. That's what this is leading to. And that's how we get the same answer. So the fundamental theorem of calculus establishes the relationship between the derivative and the integral, and it just says that the rate of change of the area under a curve up to some point x equals the height of the area at that point. And it helps us find definite integrals. Total area. The example that we had shown you before had the function above the x-axis all the time. So when we talked about the area under the curve, it was always the area between the x-axis and the function. But what would happen if the function went below the x-axis? What would we get then from a to b? Well, what we'll find is, because we're talking about this height, and it's positive when it's above and negative when it's below, the area then below the x-axis, from the x-axis to the curve, will be negative. So if you want to find the total area, these will be positive numbers, but this will give you a negative number, and it will reduce those two positive numbers, at least by a little bit. You won't get the total area unless you split this into 3 pieces. This first one is positive. The second one that you'll have to take the opposite sign because it'll be negative, and the third one that's positive. And so you'll have to know what these things look like. That's why you learned all that graphing in the other courses before you came to Calculus 2. So On page 288, excuse me, number 40, we can look at a function y equals x cubed minus 4x. And we want to do this for a negative 2 is less than or equal to x, less than or equal to 2. So it's from a negative 2 to 2. If you would graph this, the graph would look something like, let's see, this goes up to 4. No, I'm sorry, 3. And negative 3. And this, so if you'd put it at 2 in, 2 cubed is 8, minus 4 times 2 is 8. That's where you'd get a 0. For a positive 2 or a negative 2, you'll get a 0. This one goes up to, and probably a little past 3, then down to 0 at the origin, and then a little past 3, and then back up. So this area is positive on the left. The area on the right is also negative. Now, if you knew that these were symmetric, you could say, I'll take just double this first one. You're not always sure. That's where being able to determine whether something has symmetry with respect to the x-axis, y-axis, or origin could be helpful. But you can just break this up. You take it from a negative 2 up to 0, and then from 0 to 2. So let's see here. So we take it from negative 2 up to 0, the function, which is x cubed minus 4x, that thing dx. You add to that from 0 to 2, the same function, x cubed minus 4x dx. Well, you just have to find this antiderivative once. That's what's sort of nice. What is the antiderivative? In this case, we take and add 1, x to the 4th, divide by that new power, minus 4x add 1, so it's x squared, divide by the new power. So that is the antiderivative. We're going to evaluate that from a negative 2 to 0. And then what we should do here is not say plus, we should say minus, because this will be a negative area, minus the integral from 0 to 2. Oops, sorry. It should be the antiderivative, which is x to the 4th over 4, minus, but since we're subtracting, it'll be plus 4x squared over 2, and this will evaluate from 0 to 2. So plug in a 0. When you plug in a 0, you get zeros for both those. Now you plug in a negative 2. A negative 2 to the 4th is a positive 16. So 16 over 4 minus a negative 2 squared is a positive 4 times 4, or 16 over 2. Minus, plug in a 2 for this one, and you get 2 to the 4th, or 16 over 4, plus, put in a 2, you get 4 times 2 squared is 4 over 2. Plug in a 0, both of these are 0. So, and I made an error here. Oops, gosh. Let me put that back up. Just a second. This 0, you always subtract this lower limit. So this should have been negative, and then that negative should make this positive. So let me go to this new screen, and then let me write it out. Otherwise, I'm going to confuse you. So let me try that again, because I'm sort of glad I made that mistake. It's an easy mistake to make with all these minuses and pluses. You plug in the 0 first. Let me write it out. 0 to the 4th over 4 minus 4 times 0 squared over 2. And that's when you plug in the 0. Then you subtract, plug in the negative 2. So now you get a negative 2 to the 4th over 4 minus 4 times a negative 2 squared over 2. That's just this first one. Then you're going to subtract. Now you plug in a 2 at the top. The 2 to the 4th over 4 minus 4 times 2 squared over 2. And I'm going to put that minus outside here. That's plugging in the 2, but you always subtract the lower value here, which is 0 to the 4th over 4 minus 4 times 0 squared over 2. Okay. And this has a big, because this, you're subtracting all of this stuff, and this is positive. So these become 0. We can forget them. We have a negative. Negative 2 to the 4th is positive 16 over 4 is 4. So we're subtracting 4. Negative 2 squared is 4 times 4 is 16. So this negative, and that makes it a positive 16 halves. Minus, got to be careful with these. 2 to the 4th is 16 over 4. Minus 2 squared is 4 times 4 is 16 over 2. Minus, and I guess I'll 0, these are just zeros because you're going to square the 0. 0 to the 4th power. So let's see here. So we get a negative 4. This is a positive 8. Minus, this is a positive 4, but we're subtracting it. And this is a positive 8. So the negative 4 and negative 4 is a negative 8. And that takes care of one of these 8s. But we still have an 8 left. So the answer is 8. Now you might say to yourself, gosh, I have to go through that and I don't know if that's right or wrong. Well, you can check it. Your calculator can do definite integrals. Let me pull mine over here. Let's look at clearing this out. Okay, so we need the function, not its antiderivative, the x cubed minus 4x. So x to the 3rd minus 4x. So you just put in the function. Let's make our window go from a negative 2 to 2. And then do a zoom fit. And this should give you the picture that we'd graphed. Now, find the sum for this left side. You do a second calc, number 7. The lower limit is negative 2. The upper limit is 0. And it gives you positive 4. That's right. Okay. You don't get the 8 yet because you've got to subtract this negative area. So if we work this and say second calc, Still fine to use number 7. But now if we go from 0 to 2, we'll get a negative 4. But that's a negative area. We want to add these areas together. Positive 4 is the positive 8. Does that make sense? So let's do another one. Page 287, number 8. Evaluate the integral. We need some practice here. So what we need to do is we need to find the antiderivative of this. First of all, I'm going to rewrite it because I think this will make it easier. The integral from a negative 2 to 1, the definite integral. All right, this is 2x to the negative 2 dx. So that this makes it a little easier because for all these polynomials, for each of the terms, add 1 to the exponent. So this is really 2x to the negative 1. Be careful, you're adding a positive to a negative. And divide by the new exponent. And evaluate that from negative 2 to 1. So plug in the 1. It's 2 times 1 to the negative 1 power over negative 1 minus, plug in the negative 2, 2 times the negative 2 to the negative 1. I'm sorry, this is supposed to be a negative 1 here. Over negative 1. Okay. So, this negative 1 to the negative 1 power is just, say, put the negative 1 down here, right? So 2 over negative 1 times 1 is what we get. And this is 2, and this says, this negative exponent says, put the negative 2 down here. And the negative 1, leave that alone. So we get 2 over 1 minus 2 over 2. So 2 minus 1 is 1. Pretty tough answer. Is this really true? Let's see. If we bring up our calculator again, and we put in the function, this is 2 over x squared. So let's do, see, the window should go from a negative 2 to 1. Negative 2 to, I'm sorry, negative 1. And then you do a zoom fit. And so we can see the x-axis. I'm going to make y min not 0.5, but 0. And that's just to see the negative, or the x-axis. Notice this is above also, so we want second trace, number 7, lower limit, negative 2, upper limit, negative 1, and you get 1. That's what we got also. Okay. Let's do another. How about number 18, same page? 287. Evaluate the integral. So this is the definite integral, negative pi over 3 to negative pi over 4. 4 secant squared t t plus pi over t squared dt. Well, let's see. What did you take the derivative of to get secant squared? Tangent. So this is going to be 4 tangent t plus, put this in parentheses, this is really pi t to the negative 2. So it's just the t you're worried about. So you add 1. So this is pi t to the negative 1. Divide by that new exponent. And we're going to evaluate this from negative pi over 3 to negative pi over 4. Does that make sense? Okay. This is 4 tangent negative pi over 4 plus pi negative pi over 4 to the negative 1 over negative 1 minus 4 tangent negative pi over 3 plus pi times negative pi over 3 to the negative 1 over negative 1. Okay. What is the tangent of the negative pi over 4? Negative pi over 4 is in the 4th quadrant, and every tangent of pi over 4 is equal to 1, but in the 4th quadrant, it's a negative 1. So 4 times the negative 1 plus. Now with this pi over 4 being moved to the denominator, let's put the negative out front from this negative 1 here. It's now pi over remember this exponent doesn't change that, so this is a negative pi, and if you have a negative pi over 4 in the denominator, you really get in these negatives now do cancel, and the pi's cancel, and you just get 4 because you invert and multiply. So this is going to be a positive 4 minus, so hold it, this is a negative 4 and plus 4, which is 0. Minus. Okay, let's see here. We're going to put in negative pi over 3. Well, the tangent, let's see, in this case, this triangle, do you remember this stuff? This is cosine over sine over cosine. The sine of negative pi over 3 is a negative square root of 3 over 2, and the cosine of negative pi over 3 is a positive 1/2. So it's 1/2 negative square root of 3 over 2. The 2's cancel, and you get a negative square root of 3. So 4 times negative square root of 3 plus, once again, this gets moved to the denominator, and then it inverts and multiplies, and the negatives cancel, so you don't get a 4, but you do get a 3. Okay, let's see here. This is minus, but with this negative, it's going to be positive 4 squared roots of 3 and minus 3. So this cancels, and you get a negative, but now it's positive 4 squared roots of 3 minus 3. Because that negative makes this negative. Let's see. Let me check this using my calculator. Here it is. First of all, I'm going to find the decimal for 4 times the square root of 3 minus 3. Is 3.928. Okay. When you put in this y equals, we don't have secant, so this is going to be 4 divided by the cosine. Put this in parentheses. Cosine of x I think this is going to work without the extra parentheses. So don't put that first one in. We can put the square outside here, and it will square this whole cosine x. Oh, but I'm sorry. Yes, that should work. This is 1 over cosine squared plus pi over x squared. And that should square just the x. Let me see. The window goes from a negative pi over 3 to a positive pi over 4. Just a second. Negative pi over 4. Now, sometimes what can happen here is things get rounded the wrong way, and I'll show you what's going on. If we do a second calc with this number 7, probably won't do it for me this time. Oh, we got to do a zoom fit. Just a second. Zoom fit. There we go. And we're also going to put the window so it includes the x-axis. So down here, x min is 0. Wow. It's going to make a big difference here. So we're looking at that area. Now, if we then do the second calc and do the number 7 definite integral, and we go from a negative pi over 3, enter. Invalid. So why did it say invalid? When you do this with your screen, gotta say quit. If this screen is just a little bit too narrow, then you're not going to be able to pick the point here on the left side of the screen. So we're going to make the window a little more wide from on the left side. So we need a bigger negative number. I think I can put a 5 here. And that would make it move to the left. For this one, we need a bigger negative number in the right, going to the right. So instead of doing all this, I'm going to make this a 6, I guess. Let's see if that then does it. You don't see much difference in these graphs then, but it should work when you put this in. Second calc, number 7, the lower limit is a negative pi over 3 the upper limit is a negative pi over 4 Well, it looks like we've got to go further. So I'm going to use negative 1.05. That's a little further. I'm not for the scale. Scale is going to be 1. Sorry. A negative 1.05 is a little bit further to the left. And for the other, 0.784 is a little bit to the right, negative 0.784. And see how that graphs. Second trace gets me to the calc menu. 7 gets me to the definite integral. Now the lower limit is a negative second pi divided by 3. Better work this time. Yep. The upper limit is a negative pi divided by 4. And now it can find it. Okay. If you'll notice, this is that 3.928, and if we go back to the home screen, we get the 3.928 with our 4 square roots of 3 minus 3. So I think we did a pretty good job on this one. Okay, problem number 28. Find the derivative of an integral. Well, isn't it just the integrand? This is what I was trying to get at before. We've got to make sure we don't, if this were just x and this were a constant, it is a constant, it's 1, then all you have to do is plug in x. But we really want the 3t squared when we plug in the sign. So this is 3 sine squared x. Now, one of the problems is, once you have that, you've got to remember the chain rule, because we need to find the derivative of what t is. T is sine x. So what's the derivative of sine? The cosine of x. So you get all of this. You get the 3t is sine x squared times the derivative of t, dt here. A similar problem, number 34. Find dy dx. When y is equal to the integral from 0 to x squared of cosine times the square root of t dt. So when you want to find the derivative, you take that cosine, square root, put in the x squared, but then you've got to take the derivative of that x squared times the 2x. Now, you can write this a little different too, I think. Cosine of the square root of x squared is really the absolute value of x. you can do that also. Put the 2x out front. Maybe it looks a little nicer. I don't know. Number 42. We want to find the total area. We're given the function y is equal to x to the 1/3 minus x. First of all, this all goes from a -1 up to 8. So we first need to find out if this thing is always positive. If it's always positive, we just plug it in and do that. But it may be that it goes below the x-axis every once in a while. So one way to do that is, I guess you can plot some points. You can use your calculator. Let's go into y equals, clear out this stuff. Cube root of x, or x to the 1/3. Let's put it in parentheses. Minus x outside the parentheses. We're going to do our window from a -1 up to 8. I think 1 is a good scale. Zoom, fit. See what happens. Got to wait for this to get done. There we go. Okay. So we've got a place where it's negative, a place where it's positive, and then a place where it's negative again. And all those negatives we've got to figure out and change the sign. So this goes from a -2 up to 0, it looks like, and then at 1. Let's make sure though. So first, we've got to find the zeros. If we factor out an x to the 1/3, factor out the smallest x, right? We'll get, when you divide by x to the 1/3, then x to the 1/3 over x to the 1/3 is 1, minus x over x to the 1/3. But when you get that, it is 1 minus x to the 2/3, right? So, when does this equal 0? When x to the 1/3 is equal to 0, or x equals 0. 1/3 power is the cube root. And when 1 minus x to the 2/3 equals 0, or 1 is equal to x to the 2/3, take the cube root of 1, you get 1, square 1, we've got to take this to the 3/2 power. 3/2 power here. But 1 to any power is 1, so it doesn't really matter. So x is equal to 1, which we saw in that graph. If we put that back up. 0 at the middle, so it's -2 to 0, and then 0 to 1, and then 1 to 8. So we've got several pieces we've got to work with. Now, what is the antiderivative? So first of all, find the zeros. What is the antiderivative? Of x to the 1/3 minus x. Remember, you add 1, so now it's x to the 4/3. And then divide by the new exponent. If you divide by 4/3, you're multiplying by 3/4. So this is just x to the first, add 1, x squared over the new, which is 2. So that is our the integrand that we're going to use for each of these intervals. This is the 3/4 x to the 4/3 minus x squared over 2 evaluated from -2 to 0. That's a negative area, so we can put negative out front. Then we got positive area, so it's going to be the 3/4 x to the 4/3 minus x squared over 2 evaluated from 0 to 2. And then we're going to get another negative area, so we got to put a negative out front. 3/4 x to the 4/3 minus x squared over 2 evaluated from 2 to 8. So I'm going to run out of room, but you can put these in. Be a little careful. For this first one, we're going to get a 1/4. And then we're going to get, for this first one here, a 1/4. But then we subtract a 12. We're going to get a 32 for this one when you plug in the 8, and a positive 1/4 for this one when you plug in a 2. Add all those together, you get 20 3/4. 20 3/4, which is the same as 80 3/4. And why did I write it as 80 3/4? I bet you that's what our calculator does. So let's go back to this graph, and then look at each of these and combine them. So we want the definite integral, number 7. Lower limit is -2. Upper limit. So now we need to go a little further back, I guess. This window. Oh. It is a -1, not a -2 here. -1. Let's try that again. Second calc, these signs can get really in the way. 7. Lower limit, -1. Upper limit, 0. Value. Let's clear this out again. Let's make our window go a little bit further. Like -1.1. And maybe make this go up to 8.1, just to make sure. If it's outside the window, it's going to get upset with us. Okay. Try it one more time. The definite integral from -1, yes, to 0. So we're going to get -1/4. But because we want it to be a positive area, we want to have the total sum, that's where we came to the positive 1/4. Okay, let's find the next one. If we do the same thing, number 7, and go from 0 to 1, we get a positive 1/4. This extra stuff here, it's rounding errors for this. And if we do the last part, and we go from 1, first of all 7, to this lower limit 1, up to 8, get to negative 20.25. So the 1/4 and the 1/4. And here, if we subtract 12, we get the 20 and a 4th. Came out negative, we have to make it positive. This negative is because of our subtraction here and stuff. Clicking in the 8 and the 2. So you can check your work. You got to be careful. Got to understand all that stuff. See what you can do. We'll see you later on.